Alright, so we're going to look at problem 144. Now I'm not going to write the whole problem down. I might do that on some of these, I might not do it on others. So you might want to refer to a printout of your Mastering Physics or to it in your book. The numbers I'm going to use are from my version of the Mastering Physics. I will probably, maybe in the future, consistently use the numbers from the book. I'm not 100% sure yet how I'm going to do this. I'll try to point out where the numbers are different because the software has the ability to randomize numbers so people get different problems. And all the problems, though, the first part of this is the same, where it says an average family of 4 uses roughly 1,200 liters, about 300 gallons of water per day, and 1 liter equals 1,000 cubic centimeters. So that piece of information doesn't change because that's actually a piece of information from reality that is true for all populations. So the part A of this question is taking that piece of information and parsing it for a particular town's usage. So what it's saying is how much depth would a lake lose per year if it uniformly covered an area of 80 square kilometers and supplied a local town with a population of 40,000 people. Consider only population uses and neglect evaporation and so on. So with these questions, again, the first thing I look for is ask the question, what am I trying to find? And I'm trying to find how much depth per year a lake would lose. And so I visualize this. I try to see, well, what would that look like? So I'm going to draw a little, don't want that. Bring this over here. Let's draw a little lake. Okay. And so we get over the course of the year, the lake goes down. Okay, so some depth. And so I have my lake, there's my surface to start with. We drink some water out of it, and the surface is down here in the future. Well, just looking at that visualization, I see a cylinder. And so a cylinder is a measure of volume. In this case, we're looking at a volume that's being used per year or is being lost per year, and we're measuring it via the depth. So on one side of the equation, I'm going to have a volume change per year. I'm going to have enough numbers that I can solve for the depth portion of it. And we'll look at the geometry of that as we look at this problem. But so in my head, I'm seeing a volume and I'm seeing a cylinder. The cylinder equation we'll find isn't really truly fully needed, but I think the concept of a cylinder helps this problem move along fine. On the other side, we have the people and the people's consumption. And I'm going to draw 4 people because of how the question's worded. All right. And this is just kind of what I'm thinking in the background. These 4 people, average family of 4, are having water flow from the lake to them. And they're getting liters per day. They're getting 1,200 liters per day. So I have depth per time, which is a year. Means some volume is lost per year. We can measure some volume per year. And over here I have volume per day being consumed. So I have volume per time and volume per time. So if we think of this in our dimensional units, the people are consuming in dimensions L3 t minus 1. The lake is losing L3 t minus 1. So that's going to define how I'm setting up my dimensions. Well, if I look at the very, very first sentence, the one that's given for everyone in the problem the same, an average family of 4 uses roughly 1,200 liters of water per day. So let's just write what an average family of 4 uses 1,200 liters of water per day, and average per 4 people, right? And so that first sentence can be turned into this fraction, 1,200 liters per 4 people per day. So we have a number now that represents the consumption of 4 people. But we want to get volume per unit time. We have volume per people per time. So I need some number in the problem to cancel out people. So the first sentence I have there, so let's look at the rest. So 80 square kilometers, well, that doesn't cancel out people. Supplies a town with a population of 40,000 people. So if I multiply this by the 40,000 people, I get liters per day, and that's a volume per unit time. So I'm creating the left-hand side of my equation just from the numbers that are in the problem. And I'm trying to get the units such that I'm going to be able to get an answer. Now, the question itself, if we look at it, is asking for centimeters per year. So we're going to want to get this in a way that's useful for centimeters per year. And the one thing is we have a nice conversion factor here. 1 liter equals 1,000 cubic centimeters. So if I take 1,000 cubic centimeters per liter, I'm in the unit that I want in the numerator, centimeters cubed. I'm really close to where I need to be. And so the last thing I need to do now is get days to year. And so there are 365 days per year. And this should set up the left-hand side of my equation. And this is what we're going to have to try to get the lake volume per year to equate to, so we can solve for that depth. And so we're piecing it apart bit by bit, and we're looking at the words. We still haven't used the 80 square kilometers, and we're not sure how this relates to depth yet, but we know how the consumption of an entire town is happening outside of the lake. So let's look at our units to make sure we have unit consistency for what's going to be the left-hand side of our equation. So the days here cancel with the days here. The people here cancel with the people here. And liters with liters. And so I'm left with centimeters cubed per year, which is L3T minus 1. So I've got a left-hand side to my equation. And so now we're going to work on the right-hand side. And that means we're going to be looking at this cylinder to see if we can get solve for that cylinder. Well, I know that the volume of a cylinder is pi r squared times the depth. But I don't have the radius or the diameter. And if I look at that equation for a second, though, pi r squared times the depth is the volume of a cylinder. But this part here, pi r squared is the area of a circle. And so what we have happening in a cylinder is that the volume is the area times the height. Well, I have this area times the height. The 80 square kilometers is an area times the height, or an area. So I don't need to actually know the shape of my lake. If I know the surface area and I multiply it by the depth, I'm going from an L2 to an L3. And so my dimensions work out. I like to visualize it as a cylinder because it helps me see it as a volume. But the actual way the problem is worded, I don't need to know the shape of it. I just need to know that it's a surface area times a depth. So I can put an equal sign here. And the right-hand side of my equation, I'm going to scroll down here, is my 80, let me make this look like the water, 80 kilometers squared per year. And I'm probably going to want this in centimeters cubed. So I'm going to be doing my depth in centimeters. So I need to change kilometers squared to centimeters squared. And I do this with two conversions. You can kind of do it in one if you blended it together. That's a little bit of memorization and work, so I'm going to do it in two conversion factors, and we'll let the calculator do my work for me. And so I want meters up top, so 1,000 meters per kilometer. But this kilometer is squared, so I square all of this. And then I want 100 centimeters per meter, again squared, and then this whole thing's going to be times depth. And so I am now set up that I can find the depth in centimeters per year. I have my equation, and so now I'm just going to want to solve for D. Now all of this stuff here becomes a number at the end of the day. I'll double check my units. Kilometers squared. We'll cancel the kilometers here that are squared. And the meters squared here, we'll cancel the meters squared here. So I'm going to have centimeters squared per year is the unit I'm going to end up with at the end. In fact, this year bit here, depth per year, doesn't actually need to be written. It can stay on the left-hand side because I'm not actually measuring it in what I measured. So I guess it would be a little fallacious to say that I have a per year over here. I am actually measuring, or what I can measure are these. And when I left with the units behind, my per year stays behind. So to be pedantic in the equation, I wouldn't put the years over there. But we're good. We have what we need here. So let's solve for D. All of this stuff is a number. It's all in the numerator. So when I divide this on the other side of my equation, so this is up here is my left-hand side of the equation, LHS. Down here is my right-hand side of the equation. My variable of interest, the thing I'm looking for, is D. So I will need to divide all of this stuff in the yellow here off of my left-hand side. And when I do that, I still have my numerator from the left-hand side. So I'm just going to put all of this in here with the units that are left behind. 40,000 times 1,000 times 365. And that's in units of centimeters cubed. All over, let's see if I get a straight line without. Still have 4 down here. But I'm now dividing by all of this. So this is going to be times 80 times 1,000 squared, because of the squared up here, times 100 squared equals D. So this division comes through. This is nice. I can punch this in on a calculator. And I punch it in on my TI-89 here. And I get 5.475 centimeters. Oops, this was centimeters squared per year. The centimeters squared came from here, and the per year was left. Centimeters per year. Now, the book says it wants one significant figure, and that's actually coming from the fact that we're doing multiplications, and the 80 square kilometers is only measured to 1 sig fig. So that's why they're reminding you to do 1 sig fig. So that's 5 centimeters per year. So the lake's going to go down 5 centimeters per year. I think your fingernails actually grow faster than that. But it's still a considerable volume of water coming across. And this is an example of how units can set up a solution to something, and you can look at how we measure something to get an answer to a problem.